Okay, so I'm sharing the screen. So basically, in the Verilog related program, we'll use this Xilinx Vivado and Questa SIM model SIM we can use. But I have Questa SIM. Okay, I'll show you the program related to this basic gates in Xilinx Vivado and as well as in Questa SIM I will show. Okay. Yes, my screen is visible now. Yes, give thumbs up. Anyone? Yes. Okay. Thank you. I will open this 1 second. Um, okay. You already all are having some idea about basic gates, no? That is there in the that you will get in the digital electronics. Okay, this you will get in the digital electronics. Okay. 1 second. I am opening that project. 1 second. Verilog programs. Verilog programs. All gates. Second. Ah, here you see all gates. I am using data flow modeling. Okay, I am using data flow modeling. Okay, data flow modeling is nothing but
Yes,
what?
sir.
Yeah, data flow modeling.
Verilog like
Just mute yourself. Just I am telling the tool. Just mute yourself. I am opening the tool. This is I am opening the all gates. Just I will explain this tool. Okay. Second, DFM is not opening. Okay. 1 second. Okay, 1 second. GLM I will open. GLM, gate level modeling. Gate level modeling I will open.
tell.
My screen is visible, no? Okay.
Yes, sir.
Okay. Yes. You see. Yeah, this is all gates. Okay, this is the all gates. I wrote the I'm writing the program. So if you see this program, okay, if you see this program, so here I'm zooming this. 1 second. I'm zooming this. Yeah, so this is the program. So that is a module, and this is a module name all gates GLM. I'm writing with gate level modeling. Gate level modeling will be like the gate level primitive will be there. These are predefined words and or NAND nor XOR XNOR not buffer. Okay, so I'm initializing input 1 is to 0. I'm using a vector concept 1 is to 0 in. So I'm initializing the outputs, that is y and y or y NAND y nor y XOR. These are the basic gates, no? Just basic gates only I'm explaining. Okay, so and or NAND nor XOR XNOR not buffer. Okay, so that means here how this will look like: gate level primitive output and input will be there. So gate level primitive and what is the output? Y and in 0 and in 1, or also or is the gate level primitive, y or in 0 in 1, and NAND y NAND in 0 in 1. Okay, so like that I wrote
Okay.
the program and I ended the program. Okay, this is the design. Okay, this is the design. Suppose for this I need to write the test
Okay.
bench also. I need to write the test bench also. So how I am writing the test bench? Here you see I am writing the test bench. 1 second. Here I am writing the test bench. Okay, so in the test bench module all gates I am using this GLM. Here I can use GLM only. Okay, here I can use I am using GLM, no? GLM TB reg 1 is to 0 in underscore TB. Whatever the inputs are there I need to use reg data type. Whatever the outputs are there I need to use wire data type. Okay, so here wire and of TB, or of TB, NAND of TB, these are nothing but outputs. Okay, and next what I need to do, I need to instantiate. Okay, instantiation is nothing but we are calling the design. Okay, instantiation, or we can call as RTL integration. So there are two types of instantiation is there. One is connection by name and connection by position with order list. Here I am using connection by position with order list. Okay, so connection by position with order list means how you given the inputs in the design, the same thing you need to give the outputs. So in the design, how you gave the inputs, the order, this order I need to follow. Okay, that is nothing but connection by position. This order I need to follow. Okay, and after that I am using an integer data type, integer I, initial begin. This is dollar monitor is some system task. Okay, if there any change in the input, you are getting the change in the output. I am using a for loop. Okay, so for every gate you have two inputs. Two inputs means what? 0 0 0 1 1 0 1 1. I need to check for all the possible combinations. For that I am using for loop. For I equal to 0, I less than 4, I equal to I plus 1, begin, in of tb equal to I, hash 20, end, dollar finish, end, and end module. Okay, so this is nothing but test bench. Design is for designing the gates. This is nothing but simulation. This is nothing but test bench. Okay, this is nothing but test bench. So here if you want to see the design, so the design, you go to RTL analysis and you need to elaborate the design. Okay, so this is reading the net list. Just we'll see the design. After that we'll see the simulation. See here, this is the design. Okay, this is my design. Okay, so see here, so in 1:0, how many inputs are there? Two inputs are there, and two inputs are there. So AND gate, this is nothing but RTL AND. Okay, RTL OR and RTL XOR. Okay, NAND gate is nothing but what? AND gate followed by an inverter. You are getting NAND gate. Okay, NAND gate. NOT gate is nothing but directly input is given, that is I of 0 is giving. I of 0, it is coming through the inverter. That is Y naught. And next this is directly, if you are getting, this is buffer, and this is XOR gate, and XOR gate followed by an inverter, this is XNOR. Okay, sorry, OR gate followed by inverter is nothing but Y NOR, and this is XOR gate, and XOR gate followed by an inverter, this is XNOR gate. Okay, so this is nothing but, this is my elaborated design. Okay, we can see the elaborated design in the Xilinx Vivado, but we can't see in the Questa sim. We can simulate this. Okay, so I want to simulate this. So what I can do? Go to simulation, run behavioral simulation. Go to simulation and run behavioral simulation. Okay, run behavioral simulation. So you see, so here you will get the waveform. See here, so if you expand, what you are getting here in TCL console also, you can see the outputs also. Okay, in TCL console you can see the outputs. Okay, here dollar monitor, here this dollar monitor are given, no? So when it is 0 0, what are the outputs of AND gate, OR gate, all these gates you will get. Okay, in TCL console also you will get the outputs, and I can see the simulation. See here, these are the simulation results. Fit to page. See here, I am seeing for which conditions, in of, these are the inputs, in of TB 1:0. Okay, when both are 0 0, what happens when both are 0 0? So there is a line called yellow line will come. Okay, you can drag this and you can see here. Okay, so when both are 0 0, what is the output of AND gate? AND gate is 0, OR gate is 0, NAND gate is 1, NOR gate is 1. Okay, NOR gate is 1, XNOR gate is 1, NOT gate means it will give the complement of I of 0. Okay, and buffer means whatever the input is there, that you are getting. Okay, and if when it is 1 means what? 0 1. What are the outputs of AND gate, OR gate, NOT gate, NAND gate? And when it is 2, okay, when it is 2, 1 0, here see here the values are changing. 1 0, what are the outputs of AND gate, OR gate? Okay, and when it is 1 1, okay, when it is 1 1, what is the output of this AND gate and NOR gate? Okay, so these are nothing but the outputs of this basic gates. Yeah, do you understood any doubt in this? Yes. So next I will show you, one second, I'm closing this. I'll show you the basic D flip-flop code in the Xilinx Vivado. Suppose, okay, I'll close this. Mm, I'm opening, one second. Okay, RTL codes, Verilog example, Verilog code example so using Questa. Verilog RTL codes, Xilinx Verilog codes. I will open the D flip-flop. D flip-flop, I told you two types of resets are available. Okay, one is basically we are using active low reset, synchronous reset and asynchronous reset. Okay, synchronous reset and asynchronous reset we are using. Okay, so that I will tell you how we can do synchronous reset and how we can do asynchronous reset. Okay, so I'm opening this project D flip-flop. Okay, so D flip-flop, first I will tell you the synchronous reset. Okay, synchronous reset, this is the program. Okay, this is the program. So here if you see, so module, this is the module name D flip-flop D synchronous reset n. So input I am giving to wire data type, input wire clock. So this is the standard representation, input wire reset of n, input wire D, output reg q. Okay, always at the rate passage of clock, always at the rate passage of clock. If not of clock, this is a behavioral modeling. Okay, so remember, if it is a behavioral modeling, output you need to initialize as reg data type. Okay, if not of clock, q is not q is initialized to 0, else q is initialized to d. Okay, end module. Okay, this is nothing but what I told you, like in the synchronous reset D flip flop, synchronous removal and synchronous applied, both are what both are synchronous with the clock. Okay, synchronous with the clock. So basically in the industry they will not use this one. Why? Because suppose if you want to reset the circuit, okay, sometimes the clock is not working. What happens? You can't reset the circuit, no. So basically will not prefer this design, but for understanding purpose I am using. Okay, you can see the hardware also. Just I am elaborating the design. One second, I need to see synchronous, no. Okay, one second. Whatever the design you want to see, that you need to make as top module. Okay, you need to make as top module. Okay, I'll get the elaborated design of asynchronous, that I will tell you, don't worry. Here I am telling synchronous reset. In this, right click, you make a set as stop, make as set as stop.
Yeah.
Okay, set as stop and elaborate the design, elaborate the design. If you elaborate the design, so here what you are getting, you are using one mux. From the mux you are giving a reset circuit. If reset equal to 0, the output becomes what making as 0, and if reset equal to 1, whatever the D input is there, you are getting at the output. Okay, so this is the basic circuit. So one more disadvantage is you need to calculate the timing path for this path also. Okay, you need to calculate the timing path for this path also. So that is one more disadvantage in the synchronous reset. Okay, next I will show you the waveform. Run simulation, run behavioral simulation. Which one is in top? I need to see. One second. So whatever you are simulating, that you need to keep as a top module. Okay, synchronous reset only there. Okay, so see here, synchronous reset, you go to this waveform, fit to page, and see here. Here this is nothing but what this is. I'm dragging this. Here initially reset equal to 0. Okay, this reset equal to 0. Reset equal to 0 means what? So anyway output is 0 only. It is going from where to where? It is reset removal. Reset removal means what? It is going from where to where reset reset removal is there. So that means it is going from reset mode to functional mode. Okay, when it is going from reset mode to functional mode, immediately you are not getting Q. When you are getting Q during this passage of clock, you are getting the Q during this passage of clock. So that means reset removal is what, synchronous with the clock. Reset removal is synchronous with the clock, and reset applied is there. Suppose where you applied the reset, see here, I am dragging this here till here. This will be functional mode only. Functional mode means what, whatever the D input is there, you are getting the output. Okay, here this is reset applied. Okay, reset applied, if you see reset applied, one second, reset applied, I think this is asynchronous, I think so. Reset applied, one second, I need to see the simulation, which one is synchronous. Okay, okay, it's there in asynchronous. Okay, I'm doing for synchronous now. I need to make a stop module. Right click, I need to make a stop module. Whichever I'm making, these three dots are there now. Three dots shows that that is stop module. Okay, run simulation, run behavioral simulation, run simulation, and run behavioral simulation. So if you see this, this waveform, okay, this is synchronous. Okay, synchronous fit to page. Yeah, as I told you, like reset removal is synchronous, same. So that means output will change with the passage of clock. And reset applied, where you applied the reset, here you applied the reset, here you applied the reset. Okay, reset applied is not synchronous. See here, when reset is applied, the output is what, output is 1 only. The output is 1 only. When it is becoming 0, during the passage of clock, during the passage of clock. That means reset removal and reset applied both are synchronous. Reset removal, reset applied both are synchronous. This is synchronous reset D flip flop. Okay, and if you see the asynchronous reset D flip flop, asynchronous reset D flip flop. So this is main important point in the industry. They will use this asynchronous reset only. Okay, asynchronous reset, active low reset we are using. Okay, this is the program for asynchronous reset. If you see the program, module D flip flop, this is the module name. This is asynchronous reset n, input wire clock, input wire reset n, input wire D, output. This is simple D flip flop. But always at the rate, always is nothing but this is a procedural assignment. Always at the rate, whatever the sensitivity list is there, sensitive passage of clock or negate of reset. That means what, if there any change in the passage of clock, or if there is any change in the negate of clock, then begin. If not of reset, that means what, if reset equal to 0, it will force the what, it will force to Q to 0. Else it will force to D. Means if reset equal to 1, it will be in functional mode. That means if reset equal to 0, it will be in reset mode, and if reset equal to 1, it will be functional mode. Okay, it will be in functional mode. Okay, this is the basic program you need to understand. And here I want to see the design. Okay, so I am seeing the design, that is asynchronous set as stop module. You need to make set as stop module, and open the elaborated design. I want to see the design, how the design will look like. Okay, how the tool is giving the design, I need to see the design. Okay, see here. So directly reset is given through the bubble. This is nothing but what, active low reset. Okay, so if you are giving directly, it is nothing but active high reset. If you are giving through the bubble, means what, that is active low reset. Active low reset, clock D and Q. Okay, so this is the elaborated design. Suppose if I want to see the waveform, okay, simulation part. So here I am doing with what, there are two are there, like design source and simulation source. Suppose if you want to design anything, you can add here, and you can next you can create design source. Okay, suppose if you want to create any simulation source, go to simulation source and add and create the simulation source. Next you can add the simulation source. Okay, so here I am what I am doing, I am running the simulation. Okay, so what I told in asynchronous reset, reset removal is synchronous, but reset applied is what, asynchronous. Okay, that I will show you with the waveform. See here, see here. So here I'm bringing this one. Here this is what reset mode. This is nothing but what reset equal to 0, reset mode. Okay, here it is going from where to where, reset mode to functional mode, reset mode to functional mode. So reset mode to functional mode means the output is not going into the functional mode. Okay, immediately the output is not going to the functional mode. When it is going during this passage of clock only, the output is following the input. Okay, output is following the input. Okay, there will be delays there, like setup time and hold time violations are there, that will come in the static timing analysis. Okay, and this is nothing but reset functional mode. Okay, reset removal. So what I told, like asynchronous reset, the reset applied is nothing but synchronous with the clock. Okay, here reset removal is there. See here, reset removal. Reset removal. One second. This is what reset removal. Reset applied. Reset applied. It should go to, one second, DQ. Reset applied during the passage of clock only. Reset is applied. One second. I need to check whether it is synchronous or asynchronous. Okay, I need to make a stop module. No, sorry. I need to make a stop module. Asynchronous reset, that I need to make a stop module. It is showing only synchronous only. Okay, I'll show for asynchronous. Whatever the design you are executing this simulation, that you need to make a stop module. Okay, see here this waveform fit to page. So here reset is what, this is in reset mode. Okay, after that it is going into reset mode to functional mode. During this passage only, this is following the output is following the input. Okay, and where the reset is applied, here the reset is applied. Okay, if you see here, when the reset is applied, irrespective of clock may be either passage of clock or negage of clock, it is forcing the output to what, 0. So from this I can say that reset removal is synchronous, but reset applied is what, asynchronous. Reset applied is asynchronous. Okay, so like this I can write the program. Okay, so this is about the reset. Okay, D flip flop. This I can show in the Questa sim also. So Questa sim also we can write Verilog code or system Verilog or UVM. I can use in the Questa sim. Okay, so this is my Questa sim. If you want to write the program for Questa sim, what I need to do here, I need to create one second, RTL codes. I need to create suppose D flip flop is there, I need to create 3 folders, that is nothing but RTL, simulation and TB. Okay, so in RTL I am writing RTL code, and in simulation I need to make work function and do function, and in TB I need to write the test bench. Okay, so here I am using what, one powerful editor that we are using in the industry, they will use in the industry, that is GVim. Okay, GVim editor. So that program I wrote in GVim only. See here, this is GVim. This is nothing but GVim. Okay, go to editor. Whatever the program explained, the same program I wrote in GVim only. Okay, so same. This is asynchronous reset. Okay, this is asynchronous reset, active low reset, and this is synchronous reset. Okay, synchronous reset. So edit, select font size 16. Okay, this is synchronous reset. Same test bench is there. Test bench. Where is test bench? Test bench. Here. This is the test bench for what, asynchronous reset. Using for loop I wrote. Okay, using for loop I wrote. Test bench is like I didn't told test bench, no. Okay, I will explain you. Test bench the explain you. So this test bench is same for both asynchronous and synchronous. Just this instantiation will change. Okay, so module, the module name, and so whatever the inputs are there, that you need to initialize for reg data type, clock, reset and D. Whatever the output is there, you need to initialize for Y data type. I need to instantiate, this is connection by name. This is nothing but what connection by name. So that means whatever the design is there, that will come outside. Whatever the test bench inputs are there, test bench variables are there, that will come in the input. Okay. Clock generation. So initial the clock, always at the rate, always #5 clock equal to not of clock. So that means you are generating clock period for 10 time units. Okay. Clock equal to what? Not of clock, integer I, initial begin. So first I am asserting the reset. Okay. Asserting means what? I'm making as low. I'm applying the reset. Okay. Asserting the reset. Reset n equal to 0, d equal to 0. Okay. And I'm deasserting. I means what? I'm removing the reset. When you will reviewing the reset, the D flip flop will come from reset mode to functional mode. So this is the functional mode. For I equal to 0, I less than 8, I equal to I plus 1, D equal to I of 0. Apply LSB of I, and I need to wait for 10 time minutes. Again you need to assert the synchronous reset, and you need to test for some more loops. Okay. So you are giving the test cases. Okay, this is some 5 steps will be there. This is initialization, and next instantiation, and clock generation, and this is nothing but stimulus. You are giving the test cases, test vectors for the design in the test bench. Okay, so this I am going to execute in Questa sim. Okay, how to execute in Questa sim? First, so I need to go to the Fire Explorer. That path I need to go. Okay, path I need to go. Where is that path? RTL codes. RTL codes. Where is that path? D flip flop. No, D flip flop. This simulation is there. No, this path I need to copy. I need to use the CD flower brackets. I need to paste this path. Okay, paste this path. So if you press ls, these are the files present in this sim location. Okay, so I need to create the work function. For that work function, vlog dot backslash rtl backslash first I am going for synchronous reset. Okay, synchronous plus acc, synchronous plus acc. Okay, 0 errors, 0 warnings. Vlog dot backslash tb backslash forward slash synchronous tb synchronous. This also I need to compile. Okay, 0 error, 0 warnings. This I need to paste. So vsim paste this. Okay, vsim paste this. Simulation will open. Okay, simulation will open, and go to UUT and add wave. This will be added. The waves are added. Okay, add wave. After that run minus all. Okay, run minus all. So you will get the waveforms. See here, I will expand this. I will expand this. You can see these waveforms fit to page. Okay, so fit to page, you got the waveform. See here, this is reset. Reset applied is synchronous only. Okay, when it is functional during the passage of clock. Here reset removal is also as synchronous. See here, when it is functional during the passage only, this is synchronous. Okay, this is synchronous. Okay, here if you want to quit the sim, I can go to quit minus sim. It will go to the simulation part. Suppose I don't want to use all those things. Okay, I want to use only one command. Means in simulation you need to write the do file. Okay, run file. What is that run file? I wrote this run file. Okay, this is the run file. Okay, so here from where to where, from vlive work to vlive work is there. No, so vlive work, vsim vlive work, vmap work. Okay, that from here to here up to run all, I need to copy in this, and I need to save this file as run.do. Okay, so here what I will do, directly do space, what is my file name, what is my run file, rename, copy this file, just directly paste this .do. Okay, directly simulation will open. Okay, so no waveforms, fit to page, so you'll get the waveforms. You can expand and you can see the waveforms. Okay, so this is about the synchronous reset D flip flop. Synchronous reset D flip flop. If it is asynchronous reset D flip flop, for asynchronous also I wrote the do file. That is using gvim. Okay, gvim I wrote the do file. Okay, so for that also I can open, or otherwise you can write that commands. Okay, run minus all. Okay, it will quit the simulation. One second, something is happening. Just give response. Okay, one second, it stopped working. One second. Yeah, I will open Questa sim is not working. One second, I will open this one. So here first what you need to do, cd underscore that path I need to copy. Which path? Simulation path you need to copy. Okay, so you need to copy in the flower bracket, close, enter. Okay, and vlib work, you need to create the work function. Okay, in that path. Okay, already exists vmap work, do space. Okay, which file? In the do file, asynchronous, this one, just I will copy run file. This is run file. Okay, run dot do error in loading. Okay, one second. I think I'm using more. I'll close this Xilinx Vivado. Stop. Yeah, so like this you can see the waveforms in Questa sim also. Okay, so like this we can see the so better to learn this gvim commands also. This will be very useful. Okay, yes.